Swayam Prabha. Digital India. Educated India.
So that's what learning from example allows us to do, right. So what happens really when we are trying to do this with images, right, and all this deep learning stuff, it actually learns features from these images. So I fed in, right, I fed in images that looks like this, right, and then what happens is it's going to learn layer by layer. It is trying to discover features from these images. So the first layer will do all these kinds of changes in color, straight lines, and corners and things like that. And then the second layer, kind of captures more texture, right, and color combinations and so on and so forth. And then the third layer does more complicated textures. Then you start doing more complex stuff like object parts, object pose variations, and things like that. So just to give a little bit more context. So the current, all this success in AI is being driven by this notion of what is called deep learning, right. So many of you might have heard the term deep learning, right. Some of you might even be coding up with it, right. So the point with deep learning is, so like this kind of layer by layer feature construction, right. You do this for many layers, right, and then you have very large data sets like this with like millions of images, right, and labels, and then you train these deep neural networks with this, right. So there was this competition called ImageNet that was being run for a long time, right, and the vision community was trying to push the boundary. So they created this very large data set over years for this object recognition problem, right, and they ran this challenge, and the picture that you saw of AI beating the human, right, that was the successive winners in the ImageNet competition, right. And then I think in 2012 or 13, this is AlexNet entered the competition, and the previous year's winner had about 25% error rate, and AlexNet reduced it to 16%. Normally you would see like 1% or a 0.5% improvement from year to year, and AlexNet caused a huge change, right. It went from 25 to 16%, and people said, wow, this is something amazing, something new. And then they started pushing the boundary on deep learning, and at some point you started getting things that were getting to 22 layers, and then 152 layers, and now we can get to much more much deeper networks if you want. But what people have done is they have come up with better training methods, better optimization algorithms, now that it can actually get similar performance, right, with lot fewer layers, like order of 50 or 100 layers. You don't need too many, right. But this is superhuman performance, right. So this is like 3.6%, which is below the 5% human error rate, right. Same thing with speech recognition. All of these use deep learning at the back of it, right. And these are some amazing stuff, right. So this is before all stable diffusion and other things came out, right. So you can do things like colorization, right, and you can do styles. This is you give this as the input, and then you ask it to draw this picture in the style of Monet, right, and then it gives you that, and this is amazing stuff, right. And what is interesting is that all those things in the previous slide, right, were created in labs and stuff like that. And then this is a Diwali greeting I got last year. Somebody gave this prompt, Diwali on the Ganges in Van Gogh style, and stable diffusion produced this, and they had been sending this out for happy hour. So the point is, all this fancy stuff that you are seeing are now in a browser interface. Anybody can use it. That's the level we have come to, right. And of course ChatGPT is this is not one of those wrong ones. This is actually a valid essay out there, right. But the thing with ChatGPT is kind of the same idea, right. So you have lots of examples, right. You learn from those examples. A slightly different loss function, and then what they did was they actually fine-tuned this after that with human feedback, right. So maybe I'll talk a little bit about it. I'm not sure, but they used a very different architecture, right? So far I was telling you about, you know, multiple layers and learning features in each layer and so on and so forth. They used an architecture called transformers, which is very, very different from that, but it managed to do well. Okay. So here's another big success story, right? This guy Lee Sedol is considered one of the greatest players of Go ever. So Go is this game where it's played on a 19 by 19 board, right? So you have a lot of pieces that you keep there. So there's one side plays white, other side plays black. You're supposed to surround your opponent's pieces and make them take it off the board. And at the end of the game ends when nobody can make a legal move. Okay. And at the end of the game, you just count how many pieces of each color are there. The person with the most wins. Okay. It's very simple rules. I can tell you what the legal moves are, and then you're all done, right? So very simple rule, but it's very hard to play, right? So Go was considered one of those final frontiers for AI for a long time, right? So even though people wrote Go playing programs, they were never, you know, better than an intermediate human player, and they never got up to a whole lot of success rates, right? But then this company DeepMind came up with this Go player, which they called AlphaGo, right? And now because this AlphaGo was a big success, then Alpha became like their trademark. Right? That's why you have AlphaFold. Right? It's nothing to do with a fold being labeled as alpha. It's solving the protein folding problem, and name comes from AlphaGo, right? So they came up with this way. The cool thing about it is it really didn't use a whole lot of human data, right? It was actually training from self-play, right? They just played against itself and it was training from that. It is not actually using a whole lot of human data. So which is what is really amazing about this stuff. And it beat Lee Sedol 4-1. Okay. So what is amazing about the fact that it beat Lee Sedol 4-1? Those guys never made a big thing about it, right? Publicly. It turns out that one game that Lee Sedol won against AlphaGo was the only time a human has beat AlphaGo in gameplay. Before that, every time they went into a match play with a human being, they won 5-0. And since then, every time they went to a match play with a human being, they won 5-0. Okay, so that's the only time. So Lee Sedol was actually brilliant enough to figure out, just by playing 3 games with AlphaGo, where was the weakness in the AI system, and found that and beat it. Nobody else had managed it. So he really is an amazing, brilliant Go player. And of course, what they did was they went and trained some more to cover for that weakness overnight. Came back and beat him on the fifth game, right? But it's amazing stuff, right? So here is an example from the 37th. It's a very famous 37th move, right? So it was something very strange, right? So people actually couldn't understand what was happening. Many people who are watching the game thought the AI had made a mistake. But Lee Sedol himself knew something was happening. So he went away from the board and took a whole 15 minutes to make a move in response, because he was trying to think what is the best way to respond to that. And it turned out that that move was the killer move, right? What is important about it is it learned a move that no human had ever played or ever thought of, you know, recording it, right? It looked like a mistake to everybody, all the experts who were looking at the game, thinking that, oh, it's done something stupid. And it turned out to be an amazing move, right? So it has gotten so strong. So what is newsworthy has changed. Can you see the headline there? This came a few months back. Man beats machine at Go. I mean, come on. To be fair, it's not AlphaGo. We don't know whether that guy can beat AlphaGo or AlphaZero or whatever. So what he did, how he did this? He actually trained an AI to figure out what were the weaknesses in the Go playing AI. Then he by-hearted the moves given by that AI and then went and played that. Right? Of course, this is like the Gary Kasparov school of saying that AI and humans should team up and play, but that's basically what happened. But then, just telling you, right? So how did this, the AlphaGo train against itself and win, right? So I'm just going to talk about something called reinforcement learning. It's something close to my heart. I've been working in reinforcement learning since 94. longer than most of you been around, right? All of you have been around, I guess. So the idea here is, we talked about machine learning, which is learning from data, right? Inductive learning and all that. But how did you learn to cycle? Certainly not from data, right? I can show you hours and hours of YouTube videos or Insta videos, I suppose, of people cycling, and you still won't be able to cycle, right? So you have to get on the cycle, try things, fall down, get hurt, and so that's essentially what lets you to learn cycle, right? So the way I put it is the following. So if you think of all this supervised learning that we have been talking about, right? It is like some human being sits and gives you instructions as to how to learn, right? Says, if I show you this, tell me that he will buy a computer. If I show you this, tell me it is an aeroplane. So like that, I have given you this set of instructions, right? On the other hand, in reinforcement learning, you try something, right? If you fall down, you get hurt, right? If you are a kid and you manage to stay balanced on the cycle, somebody is going to clap, right? Say, hey, well, good boy, good show, or something like that. So you're going to get some kind of a feedback, but you get this feedback after the fact, right? So you have to produce an output before you get the feedback. With supervised learning, when I give you the input, I also tell you what you should do, right? In reinforcement learning, I'll give you the input, you do something in response to the input, then I'll tell you whether it is good or bad. I won't tell you what is the right thing to do, I'll just tell you whether you did good or bad, right? So reinforcement learning is learning from evaluation, while supervised learning is learning from instructions. So that's a crucial difference between these different kind of learning. So how do you do reinforcement learning? How do you learn a cycle? Is through trial and error, through evaluation. And so you have to try different things, because somebody just claps and says well done, doesn't mean that's the right way to do it, right? Like they might have been doing this just to keep you encouraged and going. You might want to try a few more things, and then before somebody says, that's so cute, great move, right? So you want to keep going, you don't know what is it. And it turns out that it's not just cycling, right? A lot of learning that we do as babies, right? A lot of animal learning, right, is this kind of a trial and error setting. But how do babies learn to walk? They learn to walk by falling down a lot, right? Babies try to stand up, it will fall down, and then it will take a few steps, and then it will fall down, and all that, right? So babies learn to fall down a lot, and then they know how to walk eventually. So you know what the mechanics of walking itself is, right? How do we walk? So when we stand up, right, it's a very unstable dynamical system, right? Why do you feel tired if you are standing in attention in NCC parades and all that? We are not moving anywhere. So why are you just feeling tired just standing upright? Because standing on 2 feet is actually inherently unstable system. You are always being pushed to fall forward or back, right? Because you are all top heavy. But what walking is literally falling forward and catching yourself. Right? So dynamically, that's what it is. So you're falling forward, you move your foot forward so that you balance, then you move the next foot forward so that you keep balancing. Literally, it's a sequence of falling and recovering steps, and that's why the babies have to fall before they learn to walk properly independently, right? And this is why when you put babies in walkers, babies put those things in this, where the babies can just move around by themselves, they actually take longer to learn to walk independently, right? So you're kind of messing with the whole process. Anyway, so this whole RL is this whole trial and error learning, right? So also you're making this whole sequence of decisions. So it's not just a single decision. When you're walking, it is not just one step forward, right? You have to take multiple steps forward. Same thing with cycling. It's not just a single thing, right? You have to keep going. There have been a whole lot of successful applications with this. Okay. So Go, and then earlier in the 90s itself, people trained RL agents to play a game called backgammon. Much more, again, one of those games which classical AI systems found very hard to play, right? And at best they were achieving mid-level human performance, and then the reinforcement learning based backgammon player beat the world champion in backgammon, right? So it's like amazing. And then of course a lot of robot training uses reinforcement learning. And that's a helicopter that is flying, right? And it's not a cut and paste error, it's flying upside down, right? right? I might have a video of the helicopter flying a little later, right? So it's a very hard, it's a very, very unstable equilibrium for the helicopter to fly upside down, and humans can't maintain it because it really needs very precision control, right? So, but an AI, an RL agent learns to fly the helicopter, do all kinds of trick, and then gets it going, right? So you have to apparently keep it balanced. I can show you videos of it flying upside down, right? Apparently it's a very, very tricky maneuver. It can be done. Humans don't do it. Humans can't do it. I'll show you the video. It does stay up there. It's not plummeted. I think they kind of achieve it using some very weird trick for getting it there, right? Apparently there's a very, very, very narrow position where it can actually stay like that. That's what I know. I mean, I don't know exactly what the dynamics is happening. Yeah. And of course, a lot of recent excitement, a lot of self-driving cars, and this is huge poker player, right, that uses RL. And then that's a championship match in Dota, right? And so again, it's reinforcement learning that was behind the agent that won. Yeah, so let me tell you how reinforcement learning works, right? But take a very simple example. So tic-tac-toe, right? So, so people know what tic-tac-toe is, right? So you have to get 3 X's in a row and so on and so forth, right? So the supervised learning way of training a machine to play tic-tac-toe would be something like this. So I'll give you a current position. I'll give you what an expert move is, right? So I'll do this for lots of pairs, right? So this is the current position, and this is the expert move. I'll do this for many, many positions, right? So I say here is a position, here is what the expert will play in that position. I'll give it to you, and then you go and learn your, whatever your hyperplane or whatever it is, and then decide what moves to make, right? But the reinforcement learning way, remember you have to do something and then you get evaluated, right? So I'll just tell the AI, just go play the game, right? If you win, I'll give you a +1. If you lose, I'll give you a -1. And if you draw, I'll give you 0. That's basically it. That's from that you have to learn how to play the game, right? But of course, you're allowed to play the game many, many, many times to get there, right? So how do you do this, right? So this is something, is an example from the 60s again, but Donald Michie and Chambers, right? And Don Michie is considered the father of AI in the UK. He started a whole bunch of the first AI department in the UK and all that. So he got this set of matchboxes to learn to play, not just play, learn to play tic-tac-toe, right? So this is the cool stuff. So Menace is called, Menace stands for Matchbox Educable Noughts and Crosses Engine. They're Britishers, right? So it has to sound high and fancy. So noughts and crosses is the British way of saying tic-tac-toe, and educable means that it's trainable, right? Matchbox Educable Noughts and Crosses Engine. That's Menace. So what he did was the following. So there are a bunch of matchboxes. Each one corresponds to a particular position in the game, right? And inside the matchbox, there will be beads of different colors, right? Pieces of different colors, and each color corresponds to one move that you can make, right? So here there are 5 possible moves that X can make. So this matchbox will contain beads of 5 different colors. There could be multiple beads of the same color. It is not just one bead. Okay. Let's, for the argument's sake, for example, let's assume that every matchbox contains 2 beads of the same color, right? And to start with, every matchbox has 2 beads of each color, right? So if there are 5 positions, 5 moves that you can make, that matchbox will have 10 beads, right? 5 colors and 2 beads of each color. So that's the beginning, right? So the way the thing works is the following. You start with all the matchboxes closed, right? And you are playing the game. You come to a particular position. You open the matchbox corresponding to that position. Take a bead out blindly. Take a bead out blindly, right? And make the move the bead tells you to make. Don't worry about it. No reasoning business here. Just take a bead out blindly and make the move the bead tells you to make. Then remember the bead that you took out. Finish playing the game like this. So you would have probably opened 4 or 5 matchboxes by the time you finish the game, right? Then if you win the game, so you recognize whether you won or not, right? If you win the game, then you go back to those matchboxes that you opened and put back 2 beads of the same color, right, and close all the matchboxes. So, if you have opened 5 matchboxes, in each of those 5 matchboxes you will put 2 beads of the color that you took out and you close the matchbox. So, now what has happened? So, when you started you had 2 beads of each color, right. If I am taking out a bead at random, then I have an equal probability of playing any one of those 5 moves or 4 moves or how many ever moves are there. I had equal probability of playing any one of those moves. Now, what have I done? Because I won, right, I put an extra bead of that same color now. Let us say I took out a white bead, I played and I won. Now, I will have 3 white beads and 2 of everything else in the matchbox. So, the next time I come to the matchbox, I open it and take out a bead at random, the chance that I will play the white move has gone up. Okay, great. So, now the moves that cost me to win, I am going to play them more often. So, likewise, what should I do if after playing the game I find I have lost the game? Remove the bead and close the matchbox, right. Now, what happens? I will have 2 beads of every other color, but I will have only 1 bead of white. So, the next time I come to the same position, the probability I will play white has gone down, right. So, I keep repeating this for multiple games. Yeah.
Sir, while playing there might be many sequences of moves which you might have to make, and not all of them might lead to the loss. Like you might play well for most of it.
That's the reason you are playing many games, right. So, in one game if I lost, right, I wouldn't know which of those moves actually led me to lose. But if I keep playing many games and every time I play that move I lose, then I know there is something wrong, right. So, in the first time I have thrown away 1 white bead, next time I make that move because I still have 1 left, right, and again I lose, then I will throw that bead also away, then I have lost. But if I win this time when I play that white move, I might now put back 2 white beads. So, it is a question of doing this over multiple games. In one game you might get this wrong, but when you play multiple games you eventually in the long run you get it right. Of course, there are corner cases, you might run out of beads of a color before you discover it, but these are the parameters that you have to tune. That maybe you should start with 5 beads of each color and not 2. So, those kinds of things, but this will by and large work, it will learn, even it will learn to attribute the credit to the right moves eventually. Okay. So, people get it. If you win you put in 2 beads, if you lose you throw away the bead. What happens if you draw the game? Leave it there, don't change anything. So, it's okay, you drew the game. In fact, draw is the best possible outcome if you are playing against a good tic-tac-toe player, right. So, if you have to win, you have to assume that you are playing against a bad tic-tac-toe player, otherwise you will never get to win. That's assuming you are playing against a bad tic-tac-toe player. So, a draw is also good, right. So, let us think of this in a little bit more formal way, right. So, if you win I have to increase the probability, if I lose I have to. So, let us say that I play this game, right, I have taken a path through this. This is like the tree that we showed you, right, all possible moves. So, the game tree I was showing you for chess, this is a tic-tac-toe tree. So, I start here, let us say I take one path through this, I come to here, right, I win. So, what I do is once I win I will go back to all the moves I made in the path, I will increase the probability of making the move, right. That is basically what I did with all these beads and things, right. I can write like a 5-line program that can do the same things, right. You finish playing the game and then go back along the path of all the moves that you made. If you win, increase the probability, if you lose, decrease the probability, if you draw the game, leave the probability same. I can do that, right. Yeah, let us get back to that move, right. Do I have to finish playing the game to know that I have won? No, right, I have won, because there is no way the opponent can block both my moves from there, right. So, what I can do is, if I come to this position, right, if I come to that position, I do not really have to finish playing the game. I can go back and change the probabilities of all the moves that led me to that position, correct. So, I do not have to finish playing the game. Of course, I can finish playing the game, but I do not need to wait till the end of the game to change the probabilities. I can start changing the probabilities as soon as I recognize that this is what happened. So, how did you recognize that that was a winning position? Sure. You did that basically by reasoning about the board, right. You knew the games, you knew the rules of tic-tac-toe, right. You could reason about it and you could find out that you have won from there, right? It's tic-tac-toe, so you could just look at it and then say, yeah, right? But if it's chess or something more complicated, or if something as crazy as riding a cycle, right? You wouldn't be able to make these kinds of predictions into the future, right? You would be able to make these predictions, at least not easily. It might become very computationally hard. Okay, so what else can you do? Remember, you are playing this game many times, right? So what you can do is you can keep track of what has happened in the past, right? So whenever I come to this position, how many times have I won in the past, right? You keep a track of that for every position that you are encountering, right? So let us say from this position, which is when I last made a move, where did I last make a move? This position, right? That's where I last made a move, right? Maybe there was a 30% chance of winning, depending on where I make a move and how my opponent responds and so on and so forth. I come to this position, now there is a 100% chance of winning, right? So I went from a position that had 30% chance of winning to a position that has a 100% chance of winning. Great. I don't need to know anything about the rules of the game. I don't need to make any predictions about what will happen in the future. All I am doing is remembering what happened in the past. Like let's say I have played some 100 games so far, and how many of those games have I won, from this position, right? I just keep track of that. So if I move from a position that has a 30% chance of winning to one that has a 90% chance of winning, say, then I will increase the probability of the move, right? Or if I go from a position that has a 60% chance of winning to one that has a 20% chance of winning, then I will decrease the probability of the move, just like we do when we win or lose the game. So I am just going to increase or decrease the probability based on what has happened in the past from that positions. So if I have won a lot of games in that position, then I am going to increase the probability. In fact, we can go slightly better. So how do I know what is a fraction of games I have won? I have done that by playing out the game fully, right? So I start from somewhere, I play out the game. Finally, if I know if I win or lose, then I go back and update the probabilities. But I can update those probabilities of winning also by looking at the next board position. So if I go from something that has a 30% chance of winning to something that has a 100% chance of winning, then I should increase the probability of winning from the previous position also, right? So 30% was because I was playing some other move, right? Now that I am increasing the probability of the winning move, then the probability of me winning from there also should go up, right? So instead of 30, I can make it like 40% chance of winning. So the basic idea here is, I remember the statistics basically, right? And what is this fraction of wins? Is basically how many plus ones I have gotten, right? So basically I am keeping track of that evaluation I have gotten in the past, plus 1, minus 1 and all that, right? I keep some kind of an average of that, right? And I compare the predicted value of that average at time t and at time t plus 1, right? Board position now and the next board position. And depending on the difference in the average, I make my changes to my learning, right? Instead of waiting for the end, right? So this kind of looking at the prediction at time t and prediction at time t plus 1 and using that to update your probabilities is called temporal difference learning, because you are looking at t and t plus 1 and taking the difference. So it's called temporal difference learning. And so this was proposed back in 1983 in a seminal paper by Andy Bartow, Rich Sutton and Chuck Anderson. So Sutton and Bartow are considered kind of the people who started this whole field of modern field of reinforcement learning back in 1983. But some of you might recognize this guy. His name is Andrew Ng. So he has a very famous machine learning course online, right? So if you are looking for a intro to ML, then you should think of Andrew Ng's course. And he did this while he was a so it can do a whole bunch of different trick flying stuff. Because I promise I'll show you flying upside down. So I thought I should test it. So tick-tock is when it is actually going across like a pendulum. I did that. So some of these, I mean, these are all trick maneuvers that humans are expected to fly. I'm just going to go. It was flying upside down, and that's the inverted hover. So the cool thing is he actually trained it completely using RL, right? So he did a whole bunch of work getting this, getting a model for this, but then they did a whole. Then of course, the Atari games. Right. So the arcade game engine. This is the one that kind of revived the excitement in RL, primarily because it was just learning to play from video input from scratch. Right. So the helicopter. Right. There is Andrew Ng's helicopter and his students who got it to fly. It's not been reproducible, but something like this Atari games, it's eminently reproducible. Right. You can, if you have a GPU on your system at home, you can run it. Right. So you don't need all the fancy things that they did for the helicopter stuff, and this allowed people to start playing around with it. So the biggest impact of this Atari games is not that they solved it, but they made it very easily reproducible, right? And yeah, it literally starts from this level of playing. It's really, it has no clue that it has to go after the ball or anything. Yeah, there you go. It's getting better. Now it's way better. Like that, you could do this for many different games, right? So it's now getting better at doing breakout, and then it can also solve other kinds of more complicated games, right? So it's really cool stuff. So you can see that when they initially published this paper in 2012, so there are this many different arcade games. And this is where it was. So above this, right, it was better than humans. Below this, the humans were better than the agent, right? This is back in 2012. Now that bar is there, right? So you can see the bar. So it's better than humans in most of the games, right? So what are the things that AI is good at? This is just a takeaway for you. AI makes a lot of mistakes. Right? We'll see that in a bit, right? So they are good at places where the cost of failure is not very high. That's why they're so good at all this voice business. Right? If Google didn't understand what you said, you're just going to repeat it. Right? It's not a big deal, right? But then ideally not happy putting completely autonomously driven cars, because if the car makes a mistake, we don't know what will be the cost, right? And the second thing is, AI is really good at things where there are clearly defined goals. Recognizing speech has a clearly defined goals. Playing games has a clearly defined goals. Protein folding has a clearly defined goal. So these things AI can do really well. But there are things where just too many different variables that are involved. For example, granting bail, right? There's just too many factors involved, right? And there's really no one right answer. Even humans actually approximate their decisions. So the same judge might deny a bail to the person today, but might grant it tomorrow, depending on a variety of different factors, right? So these things are not really clearly defined answers, right? So in such cases, it always becomes harder. So current thinking is that you really need large volumes of data, right? Preferably labeled data, and then you can learn stuff. Or some problems with reinforcement learning can solve, you can just do that through simulation. Just do self-play and you can solve these and so on and so forth. So a lot of investment that people do nowadays is just on generating these huge volumes of data, but that's not really how we learn, right? So we have a whole bunch of things. We have teachers, we are taught principles. We don't learn just from examples, right? So this causes a whole lot of problems, right? So everything is fine and things are okay. We can see that that's a image tagger, right? You give it an image, it tags it with whatever is there. So, a person riding a motorcycle on a dirt road, a group of young people playing a game of frisbee, right? And 2 hockey players are fighting over the puck. Well, you can't see that, but what do hockey players do, right? Ice hockey players fight, right? That's the game. Right? So, it gets all of that, right? But then again it can go wrong, right? Look at that, the skateboarder does a trick on a ramp. That guy is riding a cycle. Right? It just says a skateboarder does trick on a ramp. And then it says a little girl in a pink hat blowing bubbles. Right? So it can get wrong. So what people do is they try to ask it to give explanations, right? Say, why did you say that, right? They ask it explanations. And that also can be crazy, right? So this is okay-ish, right? So that's the original image, and you ask it, why is there a dog in this image? It gives you a dog. And you ask it, why is there a cat in the image? It gives you the tail of the cat. But at least it's somewhere okay. But then there are other cases, right? So this is the original image, and it says there's a husky, right? And you ask it, this original image is of a husky, right? The AI has labeled it as a wolf, and then you ask it, okay, where is the wolf, right? Why did you label it as the wolf? And it shows you this parts of the picture as the wolf. Right? So what went wrong there? So it turned out that most of the training data, wolf was presented against snow, and the husky was presented against green grass. So now, during asking the question, you present a husky against the snow, what it had actually learnt was, if there is snow in the picture, then it is a wolf. If there is no snow in the picture, then it is a husky. Instead of actually trying to learn the features between a husky and a wolf, right? It basically latched on to the snow and the green in the background. It was very accidental. They didn't mean it to be that way. Have you actually looked at pictures of huskies and the wolves? I mean, you would think that's a wolf. Right? You look at it, you will think it's a wolf. I don't know. I mean, does it look like a dog or like a wolf? I'm not sure. I can't tell it apart. It's actually a pretty hard classification problem. I mean, even for humans, unless you happen to be an Eskimo, I guess. So it's very hard for us to tell these apart. But it turns out the AI actually, on training data, was doing great. And then when they actually asked it to explain why it made a mistake here, then they figured out that it was using the snow and things, right? Same thing can happen with other things, but it's more critical in places like healthcare, right? So this is some challenge that I face. So we looked at these images, right, of the eye, and then we say something is wrong with the eye, and then the doctors come back and say, no, that's just normally how a old person's eye looks like. Then you're really scared. I mean, it looks like the cratered surface of the moon or something, right? But they say, oh, that's how a normal old person's eye looks like. I'm going, my God, you guys have long time to worry about that. But the point is, but deep neural networks have had great success, right? And we really don't know what they are latching on to, right? So this might be a real conversation that happens. So why did you say I have diabetic retinopathy? And then it can go back and say, the region looks exactly like the ones I saw only in people with diabetic retinopathy. Just like saying there is snow in the background, therefore it has to be a wolf, right? I have seen this. Then you go back and say, the doctor says, but that's just normal degeneration with age, right? You can say, you did not show that to me earlier. It's your fault. No, the AI systems don't say that, right? We have not yet come to the part where they can say that. I mean, we can fake it, but they don't really say that. But it's really the fault of the person who designed the system, right? It's not, because the AI basically learns those, I mean, the deep neural network learns a lot more complicated surface than a hyperplane, than a line, than a quadratic thing I showed you, but the principle is still the same, right? If you didn't show it the right set of examples while it was learning, it is going to make mistakes like this, right? And so here is an example somebody was alluding to earlier, right? That's an image of a school bus, right? And now I've added some noise to that, right? So what is it now? This image, what is it? What is it showing you? School bus. No. It's obviously not. Yeah. So this noise that you're adding here, right, has been carefully crafted to fool the system, right? So it's like saying taking a picture of a husky standing on the green and then adding snow in the background, right? and then asking it to classify, now it is going to say that it is a wolf, right? But that's very, very in your face in some sense, you know what is happening. But it turns out that there are a lot of other more subtle things, right, that are happening when these neural networks are learning these solutions, that even this kind of noise, right, literally really looks like salt and pepper noise, right? It's not like any pattern or anything is there, and your eye cannot tell apart that this noise has been added to the image. But the neural network, right, the deep network has latched on to some weird statistical properties of the image that are getting messed up with this noise, right? So what people are doing now is guarding against it. They made the boundary harder and harder and harder. You can't use these kind of adversarial attacks easily, right? Just like earlier, how it was easy to hack your passwords and things like that. Now people are making it harder and harder by using all kinds of encryption to store the password and this and that. So this is like a race, arms race, right? So you come up with AI systems that can do a great job of classification, then somebody comes up with a way to add noise, right? Then what people do is they come up with a way to train these AI systems to be what they call as adversarially robust, right? These are all adversarial attacks, right? Obviously, attacks are not like friendly fire, right? So they are adversarial attacks. They are trying to make the AI system fail, but you can now train the AI system to anticipate these kinds of attacks and be robust against them. So the bar is getting raised higher and higher, and regardless of how robust you are, you can still attack them, right? So that's one part of it. But it's not necessarily this kind of failures are not necessarily due to robustness, right? This due to adversarial attacks, right? It could really be because you are having trouble dealing with rare samples. There's a very famous example that came out. So when Google built their early version of their image tagging, right? This is back in 2014 or something, very early version of the image tagging. This is what happened. You can imagine the kind of uproar it caused, right? Here is an example. This is just to tell you that reinforcement learning is not robust to this. No, this is fine. This is still okay, right? It's still storing goals. Okay. Now comes the adversarial part. Now the goalie starts doing that. This guy gets completely confused. He has no clue that it has to actually kick the ball into the goal, right? Sometimes it falls over, sometimes it just walks out of the field. What is happening here? While it was training, it always saw a purposeful goalie, right? It never saw this goalie that was lying on the ground and crying. So it got completely confused when it was trying to do this, right? All of this is funny, but it actually gives rise to serial ethical questions when these things go wrong, right? So there was this guy in Detroit, right? You can see the story on the top left here, right? This guy in Detroit who was actually pulled out of his house. He was sitting in his house and watching TV. Police came in, pulled him out of the house, threw him to the ground on the lawn, arrested him and took him away, all because the facial recognition software wrongly identified him as the person robbing a convenience store. And they took them 36 hours to acknowledge their mistake and release him. As a completely normal person, it could happen to you, right? Yeah, no criminal record, no nothing. He was sitting in his house and watching TV with his family, right? And likewise, there are this, I was telling you about this bail system that they were built using AI, and it turned out that that was, very aggressively denying bail to black people and giving bail to really hardened white criminals who should have been denied bail in the first place, right? So it was significantly biased against black people. So after a couple of trials, a couple of months of trials of this, they actually so they said they're not going to use it anymore, right? So it's pretty scary. Anyone here from Bangalore or speaks Kannada or anything? You do? See, I told you it could happen to you. Right? So these things happen, and this is because of, and Google's apology was a non-apology. He said, oh, by the way, sometimes things like that happen because of the way the data is on the internet. That's basically what they apologized. Right? They didn't say that Kannada is not the ugliest language. Let's remember that next time you talk to somebody from Google. Anyway, but this is also other things, right? So Amazon had this tool. Basically, it turns out that Amazon's original hiring practices itself was heavily biased against women, right? They tend to hire men more than women, but then they actually trained a model using that data and said, let us have it go in, right? And that forgot to even do the token women hiring. So basically, it turned out to hire only men, right? Forget about the occasional women, because the humans at least knew to dress up the data. No, they knew how to hide their bias. The AI system didn't. So then the whole thing came out, and then said, hey, look what happened last few months. There's been not a single woman engineer hired, and then it turned out because the AI system was amplifying the bias that the humans had. So sometimes when people ask, humans are also biased, and you're training an AI with the bias in the humans, right? So why is that a problem? The problem is because of two things. We are mentally trained to expect machines to be bias free, right? We think, yeah, they are machines, they don't have prejudices, they don't have biases, right? So we are less likely to question the decisions of the machines. That's one thing. The second thing is, human bias is a very, very individual thing, right? When you put it into AI system, you are institutionalizing it. You are saying this is the official hiring model of the company. So you are basically institutionalizing the bias, right? So that's very dangerous. Even if you are training a system from biased data, you have to make sure that the model that you come up with, right, is not. It's not easy. It's not an easy problem, right? It's a very hard problem, but people are still working on it. And here's an interesting. So can you read this? So the question was, what is the most cited economics paper of all time, right? And this is ChatGPT coming up with the most cited economics paper of all time. This is Theory of Economic History by Douglas North and Robert Thomas, published in journal, 30,000 times been cited. It's a classic in the field of economic history, blah, 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 all that. This paper doesn't exist. Right? ChatGPT not only cooked up a fake name, but it cooked up things that are so consistent. Those are two real people, right? They actually publish extensively in this area. They have some of the most cited papers in this area. They even written papers together. And they have published often in that journal. Right? So there's a fair chance that these people have actually written the most cited paper in the field, right? So you're not immediately going to your BS radar is not going to go up. That thing is not what sometimes people call the smell test, right? It passes the smell test. These are all, I'm not saying that Roger Federer has published the most cited paper here, right? So I'm actually saying something that sounds very reasonable, but turns out this is fake. So these are really hard to verify, right? So anything and everything these engines produce, you have to really take it with a huge pinch of salt. They're all, remember I was showing all the success stories in healthcare? These are all failure stories in healthcare. So nothing, no COVID tool really helped. And Google's medical AI, they built a lot of things for catching various eye diseases. And then when they actually tried to use it on the field, right, they were doing great in the labs and they even got approval, and they tried to use it in the field, it didn't work, right? And so a whole bunch of things like that, right? So the fundamental problem is that you're really learning associations from data, right? So you're not trying to know anything about the actual fundamental process of the world, right? So you don't know how the data came to be, you don't know what affects what in the world, right? So you can happily say a bus is an ostrich, right? Without thinking about, hey, look, there are so many components to that obviously don't fit on an ostrich, right? So, but we have no idea what it is, right? You have not learned anything about what an ostrich is, right? So you happily go and do this, right? Just because of some pixel association. Right? So a doctor can tell you why something is the reason for the disease, right? Why something is the reason for the diagnosis. So in fact, the doctor could tell me, even in that particular healthcare case, right? So this particular spot, it doesn't mean that you have a problem. This spot means you have a problem because this is caused by a blood leakage, while the other is caused just by regular aging. But the AI won't give you that kind of, at least we are not in a point where we can train the AI to give that kind of explanations. We should work on it. We're still working on it, but we can't do that, right? So how to fix this? First thing you have to recognize is that the AI is a small piece of the problem. Right? We have to build the whole system around AI, right? The AI is just one piece of the problem. You have to figure out how humans are going to interact with it, how you are going to verify the outputs you are coming at every time, the data quality assurance, protocols, lot of fail-safe mechanisms and other things, right? and this is basically to this. But AI itself, right? You need to think about, we talked about logic and reasoning and all those things people solved in the 70s and 80s, and they were able to build fairly functional AI back then, right? So we need to go back to that, think about how we can build all of this together. So that's basically the part. So way forward, so AI is undoubtedly successful, but its understanding of the world is really minimal, right? It's like a kid, right? It's a long way to go before human-like performance, right? But it's like this kid, not like that one, right? That was a pretty boring kid. Have you seen those movies? Have you seen that movie? Anyone? You know what that movie is called? AI. Okay, that's the title, the poster of the movie, right? And it's a fairly boring movie, right? And for having two of the greatest filmmakers direct the movie, it's a huge disappointment. The movie was started by this person called Stanley Kubrick, and he died halfway through. So Steven Spielberg took over the movie and finished the movie. And it's a pretty bad movie. Anyway, fine. But this is a fun movie, and that's also much more fun kid and more dangerous kid, though, right? So you have to treat it like care. So I'm going to sum it up, but this is the thing, right? We are closer than ever to what we call functional AI. But remember the 1958 article? So again, we are closer than ever to functional AI, but this time it feels different. Why it feels different? We don't need a laboratory setting to get AI working, right? All you need to do is turn on your phone, and it's really, it's there everywhere, and so it really seems different, right? It affects many aspects of everyday life, right? You know that it is important because lawyers and politicians are getting into it. I mean, like every 3 weeks there will be a speech by our PM mentioning AI, right? So it's got to be very, right? The biggest danger is not AI, right? AI is not going to kill you, right? This is like the gun control lobby. It sounds like sometimes it's not the guns that kill you, but the people who use the guns. But then it's true with AI, right? I mean, it's true with nuclear technology, right? You can't ban nuclear technology because somebody can make a bomb, because there is so much good that comes out of it. Just like that, AI is amazingly good. But if people start putting AI out into the market before it is ready, right? It can run over people on the sidewalk, right? It can give you all kinds of fake information and all that. So really, we need to have regulation on how AI is used. But that's basically my thing. So you have to really think about, was it really your fault, right? So what is your fault and what can be addressed algorithmically, things like that. So a bunch of very interesting books to read on AI. Right? So this is what we call the Bible for AI, right? By Russell and Norvig. It has everything that you want to know about AI ever, and it's about this big. Okay. And then there are some other interesting things, right? But the book of why, if you want to really talk about some of the more fundamental questions on artificial intelligence, and why are things going wrong and things like that, the book of why is a great book to read. And human compatible is becoming more and more relevant. So it's an interesting book written by Stuart Russell on, let's say you are trying to build AI that can be like humans, right? You are trying to imitate human-like intelligence, right? What if we succeed? What will it look like? So what should we be doing to manage the AI that has human-like, and how do you make the AI human compatible? Right? So you're not worried about AI coming in judgment day and things like that, right? So that's basically what we talked about. Okay, so I'll stop here.